Today we're going to talk about how we use the solubility chart and how we read it. We're doing this so we're going to be able to predict when precipitates form in reactions, and our success criteria is being able to use the solubility chart to predict the solubility of an ionic compound. So this is what the solubility chart looks like. Many students feel overwhelmed when they look at it for the first time because there is a lot of information summarized here, but it's actually set up in a fairly simple way. So if you can understand how this chart works, you can use it to predict a lot of different things. At the very top row, we have a variety of different ions. In the second row, we have compounds that will be highly soluble in water. They are able to dissolve. And then in the bottom row, we have compounds that have a low solubility in water. They are not able to dissolve. Now, we say low solubility for this level, not no solubility, because in reality, they do dissolve in water a little bit. But for all practical purposes, we can pretend that they don't. So that's what high solubility and low solubility really mean. They're able to dissolve in water, or they can't. So let's look at this in action. The very first ion we see here is the ammonium ion. Now the ammonium ion in its high solubility row says all. What all means is that pairing any ion with ammonium will produce a compound that is soluble in water. So since ammonium is a positive cation, you can pair it with any negative anion and all of them will be soluble in water. Then under the low solubility row, it says none. That means that none of the anions that pair with it create a compound that are insoluble in water. The same thing is true for nitrate, chlorate, and perchlorate, although because these are negative anions, they're put in a separate column because everything pairing with it will be a positive cation. But all the cations that pair with them have high solubility, none of them have low solubility. Moving on to our next column, we see the acetate anion. Note that sometimes you'll see acetate written differently. Sometimes it's C2H3O2 negative. It's the same thing, we prefer this way, but both of them are valid. So for acetate, under high solubility, it says most. That means most positive cations you pair with this anion are able to dissolve in water. But then what ones don't? Well, we can see that in low solubility, because low solubility lists the silver ion and the mercury 1 ion. These two ions will form compounds with acetate that are not soluble in water. So silver acetate is not soluble in water, and mercury 1 acetate is not soluble in water. Everything else, most acetate ions, are. Similar sort of thing with the chloride, bromide, and iodide ions. Most compounds they create are soluble in water, except for these exceptions. Same thing with sulfate. Then we move on to the sulfide ion. Now the sulfide ion has most under the low solubility. So that means for sulfide, most ionic compounds are not soluble in water. Which ones are? Well, anything containing group 1. Remember, group 1 is your first column in the periodic table, so your sodiums, your potassiums, your lithiums. Group 2, your bariums and your calciums. And ammonium. Everything else, oxide is group 1, ammonium, strontium, barium, and tellurium. Everything else does not dissolve in water. And then for carbonate, phosphate, and sulfite, it's just group 1 and ammonium. You'll notice as well here there's a couple of repeating patterns. Ammonium's always soluble in water, nitrate's always soluble in water, but so are the group 1 ions, at least for any purposes that we're going to deal with in high school. Then, if you need to read this instead of listening to me, this slide is just a simple summary of how the chart works. So if you need to, you can pause the slide here and read through it.